and good day to you. Today we are doing the fundamental theorem of calculus and how that relates to particle motion, and we're also touching on average value today. So let's talk about, first off, position, velocity, and acceleration. Now, we always say those things in that order, and I'm going to write them down in that order, just kind of like off to the side. So let's put position first, and then velocity, and then acceleration. Okay, if you start with position and take one derivative, you get velocity, and then take another derivative and you get acceleration. So this is one of those charts where as you move down, that is taking the derivative, and I'm gonna put dt instead of dx because usually these functions are written with t as your main variable. Now, if you move down the list, you get derivatives. If you move up the list, you would be taking integrals. This means that if you start with a velocity function, and that is the little guy that's inside of your integral, so that would be your integrand, you take one integral or one antiderivative and you get your position function. If you start with velocity and you want acceleration, you take one derivative and you've got acceleration. Okay. So our very first piece of information here, one of the three things to keep in mind is that the integral of velocity is position. And then if this is a definite integral, the b up here would go here and the a from here would go here. So this is literally the fundamental theorem of calculus, just specifically with velocity and position. Cool. Numbers 2 and 3 talk about distance that is being traveled. If we are given a velocity and we want to find a distance, whether it's net distance or total distance, we are going to be taking the integral, because the distance between where a particle starts and where a particle ends is going to be the difference between their two positions, right? Take where you start, take where you end, and subtract the two, and that's how far you've traveled, as long as you're traveling in the same direction the whole time. So that's the difference between net and total distance, is whether or not you switch directions. So right here, this integral is the same as this integral. So that means that we have P of B minus P of A is your net distance. Net distance represents how far it is from where you started, P of A, to where you ended, P of B. In this example, our velocity is positive to begin with, and then it becomes negative. Okay, it's the same picture on both of these. This one's going to be for number 2, and this one's going to be for number 3, 2 and 3. Okay, in this picture, A and B both have positive velocities. That means that we are traveling to the right this whole time. Here, our velocity is 0, which means we are stopped. And then our velocity is negative, which means we are traveling to the left. Okay, so we switch from traveling right to traveling left. Since we are traveling right this whole time and we're not switching back and forth, really we just need to find P of B minus P of A, and we're done. We found the net distance. It also happens to be the total distance because the velocity is greater than 0 on this entire interval. Number 3, if we want to find the total distance that the particle travels, we have to include an absolute value, and here's why. Let's say that you are running just like around. You're running like back and forth. We talked about a cat before, right? Running back and forth. If the cat starts here and then goes left, right, left, and then ends over here, it's traveled quite a bit. Like it's burned a bunch of calories going left, right, left, right, left. It should get credit for all of that. That would be a total distance, adding up everything. But if the cat begins here and ends here, just using the net distance is going to find this one distance. It's not going to account for the fact that the cat moved back and forth in between. So that's where this absolute value bit comes in. let's take a look at this V of t graph. We are going to take the absolute value of V of t. That means that anything that was negative before is now going to become positive. So I'm just going to flip this straight up. So it's something like that. More or less, that's pretty decent. So this piece that was down below gets absolute valued, and it comes up to the top. This was all positive area to begin with. But this was negative area, so those areas would cancel each other out. We all know about adding positive and negative areas together. So when we flip this up, it now becomes a positive area. Ooh, so we are finding this being absolute value of V of t. We're going to find this area from here to here. Okay. What we need to pay attention to with total distance is where does the graph of V of t actually touch the x-axis, well, t-axis, I guess. And that portion, like down here, is what gets flipped up. So it's not so bad when you are looking at an actual picture, or if you can plug something into your calculator and have it do the absolute value bit for you, that's not so bad. Let's take a look at some problems. Hopefully this will make a little bit more sense. Number one, the velocity of a particle that is moving along the x-axis, so that's our cat, right, moving back and forth, is given by the function v of t equals 3t squared plus 6. You would not be able to use a calculator on this problem if it was on the AP exam. There's different sections where you get to or don't get to use a calculator. This was grabbed from a non-calculator. So part A, if the position of the particle at t equals 4 is 72, what is the position when t equals 2? All right, so we have P of 4 equals 72, and we want to know what is P of 2. Well, we've done problems kind of like this in a slightly more recent section. We have looked at how if we've got P of, if we take the integral of P prime of t dt, that's going to equal P of t, right? Integral of a derivative is the actual function itself. Okay. But things to notice. The derivative of position is velocity. So instead of P prime of t, I'm going to put V of t dt. And since we have numbers here, those t values of 4 and 2, instead of putting P of t, we want to put P of 4 and P of 2, and we just have to figure out the correct order. It is pretty much always easier to put the bigger number first and the smaller number second. So 4 is going to go here, and 2 is going to go here. If 4 is here, then it was on the top, and 2 is down here at the bottom. So this right here is that fundamental theorem of calculus. P of 4 we know is 72. P of 2 is the thing we're solving for, so minus P of 2. And over here we want the integral from 2 to 4 of V of t. Well, we are given the function for V of t. It's 3t squared plus 6. Ooh, integral from 2 to 4 of 3t squared plus 6 dt. We can take this integral using our power rule. Becomes t cubed plus 6t, and normally we would put a plus c, but we're evaluating, so we don't have to put plus c. We're evaluating from t equals 2 to 4, and that just bring down the right-hand side. Okay, left side, we're gonna plug in 4 into both of those spots, and then a minus, and then plug in 2 into both of those spots. So I'm gonna do my bracket thing that I always do, bracket minus bracket. This will be 4 cubed plus 6 times 4 minus 2 cubed plus 6 times 2. And then I'm going to bring the next line up here. Okay, 4 cubed is 64. 64. 6 times 4 is 24. 2 cubed is 8. And 6 times 2 is 12. So we've got 64 plus 24, that would be 88. Minus 8 plus 12 is 20. So this is 68 equals 72 minus P of 2. Solving for P of 2, we can add P of 2 to both sides and subtract 68. P of 2 equals 72 minus 68 is 4. Yay! So the position of the particle at t equals 2 is 4. Cool. Next problem, what is the total distance the particle travels on the interval from 0 to 7? Total distance equals some kind of an integral. We already talked about that. So the integral for total distance, that's the one where we have the absolute value, because we have to make everything positive to count where we travel left and where we travel right, where all that switching direction stuff is. So total, we need everything positive. So this will be absolute value of V of t. We're told that we're looking from 0 to 7, so I'm going to put 0 here and 7 here. All right, we need to figure out, where does V of t switch from positive to negative or negative to positive? So let's set V of t equal to 0. The goal is to break this up so we know which pieces are above the x-axis and which pieces are below the x-axis. Like this picture, we need to know what parts to flip up and make positive, so that we can split this into 2 small integrals instead of one big integral. Okay. So let's set V of t equal to 0 to find where we touch the x-axis. V of t is 3t squared plus 6. Let's solve for t squared. We'll subtract 6 from both sides and divide by 3. So t squared equals -2. And if we take the square root of both sides, we get t equals plus or minus the square root of -2. We have an issue there. You cannot take the square root of a negative number and get something real. So that means that t, or V of t, never equals 0. That's impossible. If we graphed y equals 3t squared plus 6, we would get this, right? That never touches the x-axis. This is V of t. Oh, and I guess the left side of the graph doesn't work because t has to be greater than 0, right? So it's this little piece right here. That's our velocity function. It never touches 0. It's always positive. So that means that this absolute value is kind of not necessary in this particular problem. Okay. If V of t did equal 0 at some value of t, we would split this up instead of 0 to 7 to be like 0 to 3 and then from 3 to 7. Okay, that was one of our properties that we did in a previous section. Because V of t is always positive, the absolute value of V of t is the same thing as just V of t. Let's work this out. So we've got the integral of V of t is 3t squared plus 6 dt, and we're going from 0 to 7. So this will be t cubed plus 6t evaluated from t equals 0 to 7. That means we have 7 cubed plus 6 times 7. And then over here we have 0 cubed plus 6 times 0. So this will all be 0. 7 cubed is some super giant number. You can absolutely do this by hand, not that you would really want to. So 49 times 7, 343. Plus 6 times 7 is 42. And when you add those two numbers together, we get 385. Yay. So the total distance that your particle traveled between t equals 0 and t equals 7 is 385. If we graphed V of t, which is this graph over here, well, the positive, like t on this side. And we went from 0 to 7, the area would equal 385. Cool. Next, on the back, we've got the velocity of a particle that is moving along the x-axis. So again, just back and forth, is given by that velocity function. It is not a very pretty velocity function, but we've got it. This is a calculator active question. Interesting. I wonder why. I bet we'll figure it out. If the position of the particle at t equals 1.5 is 2.551, what is the position when t equals 3.5? So P of 1.5 equals 2.551, and we are looking for P of 3.5. Okay, this right here, the fact that we have both of those, they're both P values, and we have the T values, and we're looking for one of them, that is your hint that you're going to be doing one of those integral guys, and that's going to equal P of the bigger one, 3.5, minus P of the smaller one, 1.5. And then that'll go from 1.5 to 3.5. Okay. So it's just the hint, since you got both of those, that we are going to be doing that integral. We want to know what is the position. So we've got the start position and we've got the end position. That means we are going to have the integral be the difference between them. So we just care about the net distance, not the total distance. So this is going to be just regular old velocity function. We don't have to do, and we specifically do not get to do, the absolute value on this. So we just want the distance between the two positions, net distance. All right, V of t in this problem is that 0.5 e to the t times t minus 2 cubed. Gross. 0.5 e to the t times t minus 2 cubed. Ran out of room. It's this. Okay, we do not have any kind of a rule or a formula or anything that can help us take that integral. So what we're gonna do is plug this guy into the calculator. So I'm gonna take y equals and plug in 0.5 e to the t, well, x. Move over, parentheses, t minus 2 to the third power. Okay, matches, that all looks awesome. Most common mistake I remember from last year was putting 5 instead of 0.5. Silly stuff. The e is down here on the natural log. You have to press second to get to it. Cool, so that is our y1. We're gonna quit out of this by hitting second and then mode to quit. Getting back to our main screen. To take an integral, you hit math 9, and we get this pretty picture. Our a value is 1.5, b is 3.5. We're gonna plug in y1 here, and to get that, you will hit vars, hit right to get to y vars, and hit enter once, really twice, because we are picking y1. And then we're gonna make this an x, because y1 was in terms of x, like we plugged in x's for it. Enter, we get 15.9191924, 3 decimal places because this is calculus. So 15.919. We could have actually done this on the previous question instead of doing that one all by hand, the one where we had like the 343. Except it was a non-calculator active question, so that would have been cheating. We don't know P of 3.5, so that's our variable. Minus P of 1.5 is 2.551. And then it looks like we can just add 2.551 to both sides. 15.919 plus 2.551 is 18.470 equals P of 3.5. So the position of the particle when t equals 3.5 is 18.470. Really what's happening is we're telling you how far you traveled, we're telling you where you started, and then you can figure out where you ended from there. That's it. B, what is the total distance that the object travels on the interval from t equals 1 to t equals 5? Okay, so we are finding the integral of velocity to find a distance, because that finds the difference between your two endpoints. However, we need to talk about all distances as being positive. If I traveled 3 miles in one direction and 1 mile back, you better believe I just traveled 4 miles, and I better get credit for all of them. The distance between where I started and where I ended was 2, but I traveled 3 plus 1 for a total of 4. So positive distances. T equals 1 to t equals 5. This is a calculator active question. So you are allowed to use your calculator for this. We need to put an absolute value into those, or into our integral. So we need to find absolute values. I'm going to clear all of this out. I'm going to hit math 9 to get to this. Our numbers are 1 and 5. Now we need an absolute value in here. To get that, we hit math, and then we go over 1 to get to number, and then number 1 is absolute value. So math, right, enter. Absolute value. And then we already have v of t plugged into our y equals. So I'll hit vars, right for y vars, and hit enter twice to get y1 there. Over here, put an x, enter. Thinking it is 913.067. Done. Okay, so the way that I remember this is total distance. You've got to count your positives and negatives by making them all positive. Net, or difference in position, or in physics it would be called displacement. That's without the absolute values. Okay, it's just wherever positives and negatives are. That is totally okay. All right, new problem. The graph of the velocity. Ooh, this is v of t. I know it says it here, but I'm going to make that nice and big. Velocity is in feet per second of a particle that is moving along the x-axis is pictured below. The position p of t at the particle, or of the particle at t equals 8 is 12. So p of 8 equals 12. Use the graph of v of t to answer the questions that follow. We want to know what is the position of the particle at t equals 3. So that would be p of 3 equals something we don't know. All right, let's set up an integral for this. We've got two different p of somethings. That's going to be fundamental theorem of calculus. Equals p of 8 minus p of 3. All right, that's the right side, which means the left side has to be the integral from 3 to 8 dt. Since this is p, this has to be the integral of the derivative of p. The derivative of position is velocity, so velocity goes in here. V of t. We are just trying to find the distance between those two positions, so it's not absolute values, it's just regular. Okay, so p of 8 is 12. P of 3 we don't know. Interesting. So we have to find the integral of velocity from 3 to 8. We've done this graphically plenty of times. We have looked for what is the area between x equals 3 and x equals 8, above the x-axis, but below our function. So this tells us to look at the velocity graph. And here it is. We're going between 3 and 8. Okay, so we've got our graph. I'm going to draw from 3 to 8. Just trace that x-axis, t-axis, whatever. Okay, from the 3, I'm going to draw straight up until we get to here. And then from 8, looks like we have to draw straight down. You will never draw diagonals on this stuff. So we've got this area down here, and we've got this yellow area up here. Okay, yellow area. That is positive. We need the area between 3 and 6 of this trapezoid. Areas of trapezoids. I'm going to do this in brown because brown is kind of yellowish. Kind of? I don't know. Area of a trapezoid equals base 1 plus base 2 over 2 times the height. Okay, these are our two parallel sides, so those are our two bases. Our first base is a distance of 1, our second base is a distance of 3, so 1 plus 3 over 2 times. And then the height is a thing that is common, okay? So it is like a 90-degree angle to your bases. So the height here is from 0 to 5, it's a 5. The area of the trapezoid is 4 over 2, which is 2, times 5, which is 10. So area equals 10. The area down below is a triangle. I'll do that in red. Triangle. Area equals 1/2 times base times height. It is a 2 by 2. So area equals 1/2 times 2 times 2. Area equals 2. Except the height is negative because this is below the x-axis. So that is technically a -2 for the height. Fix that. Multiplying that all out, we get area is -2. The area total between 3 and 8 is 10 plus -2, which is 8. So 8 equals 12 minus P of 3. What does P of 3 have to equal? Looks like 4. So if you add P of 3 to both sides and subtract 8 from both sides, you get P of 3 equals 4. Yay! So the position is 4 when T equals 3. The position is 12 when T equals 8. B, what is the acceleration when T equals 5? The function that we have is velocity. Velocity to acceleration, you take a derivative, right? Going through this list, velocity to acceleration, you take a derivative. We're not given an actual function like written out. We are given a graph. So if v prime of t is a of t, we are looking for the slope of velocity at t equals 5. That will be a of 5 equals. This is a velocity graph, so look where t equals 5, that's like here-ish. We find the slope of that straight line. This is at 4, so it looks like 5 over 2. And it is a negative slope. Cool. That one's done. Next, what is the net distance? Net is just literally subtract them. So positives and negatives are all going to affect everything. Negatives will like cancel out positives. It's another way to say that. We are looking for the net distance that the particle travels from t equals 0 to t equals 10, 0 to 10 of v of t dt equals p of 10 minus p of 0. There are p's here and v's here because velocity is the derivative of position. We cannot figure out p of 10 and p of 0 from this graph. Oh, hang on. We just need to find the area. We don't even need all that because we don't have one or the other, right? We're not looking for p of 10 or p of 0. We're looking for what is the area. So we just need to find the whole area. Oh my gosh, this is going to be so easy. Look, this yellow one was 10, right? And since this is reflected here, that's 10 also. This pink one right here, that was a -2. And this is reflected here, so that one's also -2. Heck yeah, okay. So 10 plus 10 minus 2 minus 2 equals 10 plus 10 plus -2, so 20 minus 4 is 16. Okay, if we cared about P of 10 or P of 0, we would plug in the one that we know and then find the other one. We don't know either, so we can't do anything. That's two variables and we don't know either of them. Last one, what is the total distance the particle travels from t equals 0 to t equals 10? Total distance. So the positives and the negatives for distance count. That means we need to make all of our negative distances positive. Absolute value of velocity, dt. T goes from 0 to 10. So all of our negative velocities have to become positive. All these little negative areas down here, we need to flip them up to the top to make them positive. So I'm going to split this where velocity equals 0. This equals the integral from 0 to 6 of v of t. Oh, why did I put that parenthesis? Whatever, I'll just finish it up. dt plus the integral from 6 to 10 of the opposite of v of t dt. I'm saying the opposite because it was below and we need to make it positive, right? Absolute value would make this negative value positive. So opposite of negative, positive. Hopefully I've said that enough times. I'm going to take that negative and move it out to the front because we can do that. So that'd be a minus there, make that a plus. Okay, now we just need areas. We know that the brown area, that's this, is 20 minus, we know that the red area, or the pink, all the stuff down below, was -4. So 20 minus the -4, double negative turns positive, that equals 24. Okay, so we traveled 20 to the right, and then we traveled 4 to the left. So you're 16 spaces from where you started, but you've traveled a total of 24. All right, let's do some more stuff. We've got one more page of notes before an AP problem. Let's see how this one goes. The table above shows the values of velocity in meters per second of a particle that is moving along the x-axis at selected values of time t seconds. So this is in seconds, and this is in meters per second. That means that position would just be meters. What does the value of 0 to 18 of v of t dt represent? I've got most of my sentence written down, so I can just kind of read it out to you. Okay. That integral represents the blank. It represents something from t equals 0 to t equals 18. I'm gonna fix that. T equals 0 to t equals 18. Because v of t is greater than 0, that integral is also the something else. All right, so since this is v of t, not the absolute value, it's going to be your net distance. It's not absolute value, so it is the net distance. It is the change in position, beginning position to the position at 18. What is your distance that you traveled? Okay, then because the velocities are all greater than 0, we also know that that integral is going to be the total distance. Okay, the reasoning again on that is because the absolute value is going to equal the actual value, what you would get normally. Everything's positive, you just add them all up. Okay. We're going to use some Riemann sums and a trapezoidal sum. I've got a bunch of this stuff already written out. Here's how I kind of set them up. I wrote out the integral from 0 to 18 of v of t dt. and then it is about. I left a little space right here, and then I put parentheses, and we have 6 sub-intervals, so I need to be able to add 6 things together, so I put 5 pluses. If you want to set that up for all of this, you are welcome to pause the video, set that up. All right, let's go ahead and work on some stuff. We are using a left Riemann sum. I'm going to use pencil so I can write all over this table and erase stuff. We're using 6 sub-intervals of equal length, and we're going from 0 to 18. Okay, so we're starting here and ending here, and we need 6 rectangles. Well, it looks like we can have 1, 2, 3, 4, 5, and 6 rectangles. Okay, we are using a left Riemann sum. That means that the top left of your rectangle, that y value is going to be the one that we use for the height. So the distance between these two numbers is the width of your rectangle, which is 3. The height of the rectangle is the left corner, 2.3. So like length times width or base times height is probably the better way to do it. The base between 3 and 6 is 3. Its height is 2.7. Between 6 and 9, base is 3, height is 2. Between 9 and 12, base is 3, height is 1.3. 15, that base is 3, height is 1. And this base is 3 and the height is 1.7. Since all of these rectangles have the same base, instead of multiplying 3 times 2.3, 3 times 2.7, and so on, we're going to take the 3 to the outside, like factor it out, and then just add up all of the heights. So 2.3, 2.7, 2.0, 1.3, 1.0, and 1.7. Okay, adding up all of those numbers. Scroll, and then multiplying it by 3, you get 33. The integral of velocity is position. The integral of meters per second will be meters. Remember when we had like position was meters, and then we're like the derivative of position will be meters per second. So we're just going backwards. We basically just get rid of one of the denominator bits. Another way to think of it, here's another way. We know that the height is in meters per second, and the width is in seconds. Miss Campbell. So along the t-axis, that's going to be in seconds, right? And the height of it is velocity. So this is time and velocity. If you find the area, you would multiply together meters per second times seconds. Meters per second times seconds equals meters. So that's going to be like area. Area ends up being a position or a distance. All right, C, using a right Riemann sum of 6 sub-intervals of equal length. Estimate the same thing. So again, all those widths of the rectangles are 3. But instead of using, for this first rectangle, instead of using 2.3, we're going to use 2.7. So this one's going to use 2.7. This one uses 2.0, and so on and so on and so on. And then this last rectangle is going to use 2.1. So we're basically just replacing the 2.3 with a 2.1. 2.7, 2.0, 1.3, 1.0, 1.7, and 2.1. Adding these all up and then multiplying by 3, you get 32.4 meters. D, a midpoint Riemann sum. A midpoint Riemann sum, we are going to have 3 sub-intervals because we have to have mid times to figure out the heights of all those rectangles. So I'm going to erase everything I've got so far. Three sub-intervals. So we're going to get 3 rectangles that are evenly spaced. That means we're going to go from here to here, from here to here, and from here to here. Okay, 3 intervals. So our intervals go from 0 to 6, 6 to 12, 12 to 18. All of those widths are 6. 6 minus 0 is 6. Okay, we're using the midpoint. So we are using the y value that is in between. So instead of 0 and 6, we're going to go halfway between, which is 3, and use its height, which is 2.7. Use the height of 9 and use the height of 15. Okay, so our heights are 2.7, 1.3, and 1.7. All of those rectangles had a width of 6. And then adding up all of those numbers in the parentheses, multiplying by 6, we get 34.2 meters. Okay, last one here. We're going to do trapezoids this time. Let's take a look at this table, erase again. 6 trapezoids. So all of those trapezoids are going to have that width of 3 again, right? Trapezoid, trapezoid. I know these shapes look like rectangles. Okay, so width of 3. That 3 is going to go on the outside. Okay. Our job is to find the average between our, the average between the heights, the two different heights of the two different sides. So like the average between 2.3 and 2.7, the average between these, and so on. So to do that, you add these two numbers together and then divide by 2. And then we'll add these two numbers together and divide by 2. You might notice that that 2.7 gets used for the first trapezoid and it gets used for the second trapezoid. 2.0 is going to get used for second and third. 1.3 gets used for third and fourth. 1.0 gets used twice. 1.7 gets used twice. But 2.1 is only the height of the last one. So 2.3 and 2.1 only get used once a piece. Okay, I'm going to show you something. It's going to make the trapezoid ones a little bit easier because they're kind of annoying. Okay, for the trapezoids, the 2.3 is first. It only got used once. The 2.7 gets used twice. The 2.0 gets used twice. The 1.3 gets used twice. The 1.0 gets used twice. All right, to finish this up, we had 2 times the height of 1.7, and then the very end height, the 2.1, only gets used once. But we were trying to find averages, so we have to multiply times a half. So I'm just going to bring that 1/2 out in front next to the 3. So this is kind of like 3 halves times, and then that whole sum. So working that out, we get 21.8, and then 21.8 times 3 over 2 is 32.7 meters. All right, so this is the shorthand way of writing 2.3 plus 2.7 divided by 2 plus 2.7 plus 2.1 divided by 2. All those little fractions. You're welcome to write them all out, but that is a lot of writing. Number F. Yep, sure, it's a number now. Find the average acceleration of the particle from t equals 3 to t equals 9. For what value of t in the table is this average acceleration approximately equal to v prime of t? Okay. Acceleration is the derivative of velocity. We are given velocity values for t equals 3 and t equals 9. So this is going to be 9 minus 3 on the bottom. Acceleration is the slope of velocity. So we need velocity values up here on the top. So this is v of 9 minus v of 3. And this equals 2.7 from the table minus 1.3 from the table. All over 9 minus 3. And this reduces to, oops, I got that backwards. Talk on it. Erase stop. 1.3 minus 2.7. There we go. So this ends up equaling negative 0.233, and we need a label, of course. Since velocity was meters per second and time is in seconds, this is meters per, and we're dividing by seconds twice, so seconds squared. Okay, according to the mean value theorem, this average acceleration should be approximately equal to the acceleration somewhere between t equals 3 and t equals 6. Okay, so this is really close somewhere to v prime of 6. Okay, it can be any t value between 3 and 9. So if we're approximating v prime of 6, we can use the average acceleration between the points at t equals 3 and t equals 9. That's it.